Hi, I'm Paul Offord and welcome to this presentation on the internal workings of Dumpcap when it's running on Windows. And we're going to look at Dumpcap running in a particular mode where it uses multiple threads. You can explicitly enable this threading mode with the -t flag in the startup command. And what we find is that a thread is started for each interface that we're recording on, and that thread gets packets from the kernel buffer and places them in a queue for processing by the main thread. So we'll look at how this all operates in a second. Now, though you may not specify the -t option, actually if you try to capture from two interfaces, two NICs, into one copy of Dumpcap, threading is enabled by default. Here we see a simplified diagram of the hardware and software. So we have the NIC, the network interface card, we have its driver, then we have the Microsoft NDIS layer. NDIS actually performs a number of functions, including normalizing access to the NIC through its hardware driver. Then it actually feeds data up through the driver stack into the other entities shown here, such as tcpip.sys and the npcap.sys driver. Now, this diagram is somewhat simplified. The NDIS driver actually wraps in and around the npcap and tcpip.sys drivers, but I've shown the drivers in this way for simplicity. I should perhaps mention that npcap.sys is the npcap replacement for the winpcap driver called npf. The other important component in the kernel is the kernel buffer, where the packets get copied from the NIC to the buffer. Let's move on to the Dumpcap process itself. So this is where Dumpcap runs. It communicates to npcap.sys through these two DLLs, wpcap.dll and packet.dll. So that gives us a nice clean interface into the npcap functionality in the kernel. Let's now consider the code running on the main thread. So the important place here is this function called capture loop start. And so eventually we enter this function, and the first thing we do is we execute gasync queue new, and that creates us the pcap queue that we're going to use later. Then we start a thread. In fact, we start a thread for each interface that we're going to use for capturing. And that's done using this gthread new function just here. And you can see that the thread will start executing at pcap read handler. So that gets us onto the other thread with the new code to be executed. The interface thread starts and executes pcap read handler, but that just does some preparation work, and eventually we end up in the pcap loop dispatch loop, which is literally a while loop going round and round. So before we go any further, let's take a look at the code executing. So here we have the code loaded up in Visual Studio, and we are actually showing it starting at the main function. I've set breakpoints throughout the code to stop at interesting places. But before we get started on that, I need to show you the properties, in particular the debug properties. So you can see debugging, and there you can see the command line arguments, and you can clearly see that I have the -t option set so that we get the threading model version. So let's start Dumpcap running and see what we get. So this is the Dumpcap window that you would see as a user, and Visual Studio has hit the first breakpoint, which is here at capture loop start. Something just to notice down on the right hand side where it says call stack at the bottom, you can see that we are on the main thread because we've entered this at the entry point W main. Earlier I actually showed you main, that's obviously another entry point, but we seem to have entered the code at W main. Now we step forward and we're now in the loop, and you can see that we're going to open a file for output by the looks of things. So that's the next thing. So we click continue. Now we are here at the point where we issue the thread call to start the new thread, which we saw earlier. And if you look 6 lines above the breakpoint, you can see gasync queue new, where we're creating the pcap queue that we use to pass packets between the interface thread and the main thread. And then we move on the main thread to dequeue any packets that exist. Let's now go back to the slides. To describe the data flow, I'm going to start on the interface thread, which started, if you remember, at pcap read handler, but that actually ends up dropping into a function called capture loop dispatch. And capture loop dispatch makes a call into the wpcap DLL, which is called pcap dispatch. That eventually ends up waiting on an object in the kernel. That's waiting on the object for some I/O to complete. We see that the NIC DMAs a packet into the buffer, and then once that packet is sitting in the buffer, the NIC will generate an IRQ. The hardware interrupt, or IRQ, is handled by the NIC driver. Now, one thing to point out is that you can have one hardware interrupt for multiple packets in the buffer. So some NICs and their drivers enable you to group together multiple packets into one interrupt. The other thing to say is that the NIC driver is split into 2 halves. There's a top and bottom, if you like. The top half that handles the immediate interrupt is called the interrupt service routine, and it's a very minimal piece of code. After dealing with the immediate matters of handling the interrupt, the NIC driver queues up something called a deferred procedure call for later dispatching and executing. So this is the way of just making sure that we return from a high priority level of the handling the IRQ down to a lower level, so that other processes and other threads within the kernel can execute. So here we see the DPC. It drives up through the NDIS, and in this case the npcap driver, and satisfies the wait object. Now control returns back to wpcap.dll. And at this point we need to get the packet from the kernel buffer into the user space, the dumpcap process address space. And so wpcap.dll in combination with packet.dll and I guess the npcap.sys driver actually copies the packet from the kernel buffer into the user address space. Now you'll notice that we have a callback function specified in the pcap dispatch, capture loop queue packet _CB for callback. So you can see the code for the callback routine above that line, and so the next thing that happens is that wpcap.dll calls into that function, capture loop queue packet callback. The first thing the callback routine does is a mem copy, as you can see, and it copies the packet from its original copy and makes yet another copy, and then it calls gasync queue push unlocked, and that creates an entry on the queue which is then linked back to this fresh copy of the packet. And I guess from a performance point of view it would probably be better if we weren't making multiple copies of the packet, but this is the way it works. So at this point we're about ready to return back to the main thread and look at how the main thread dequeues the queued packet and then processes it. But before we do that, I thought we should perhaps take a look at a different perspective of the operation of Dumpcap. And so we're going to look at how Dumpcap is working using the Microsoft Process Monitor tool. Here's a recording I took earlier of Dumpcap working with, I took the recording with Process Monitor, and I enabled thread profiling. So it's basically taking snapshots of the state of all the threads 10 times a second actually in this case. And I've highlighted a couple of threads, and I'd like to look at the stack of the first one. Now you can see that this is obviously the main thread because we've got W main in the stack, and you can also see the capture loop start, and then we see capture loop DQ packet. So we'll see what that means in a minute. So we've actually caught this thread just at the point where it's trying to DQ packets, and then you see how it DQs the packet using this G async Q pop intern unlocked call, which is a G library, a glib call. So that's the main thread. Now let's go to the other thread, and this is the interface thread that was running. So you can see pcap read handler at the base of the thread, just as we expected, because when we spun the thread up, that was the start point. And then you can see that we quickly call into capture loop dispatch, and that in turn calls pcap dispatch, which calls into the wpcap.dll, and then that in turn uses uses packet.dll, and so we go on up the stack. So here we can clearly see the operation of the two threads. So back in Visual Studio, let's continue with the execution of the main thread. So this is interesting. It's actually stopped at the point where it's trying to dispatch the packet using pcap dispatch, and you'll remember that's on the interface thread, not on the main thread. And this is one of the challenges of troubleshooting or investigating a multi-threaded application with Visual Studio. I have breakpoints in both threads, and I can't predict which thread's going to be running and which one's going to hit a breakpoint at a particular point in time. So all I can do is keep hitting continue until I actually drop into the expected piece of code. Here you see I'm still on the interface thread, because if you look at the call stack on the right, you can see the pcap read handler entry, and we recognize this as being a callback associated with the processing of the packets. And this was the callback routine that we saw called earlier, that does the mem copy and then the queuing of the element onto the queue. Let's continue again, and now we're at the point where we expect it to be. So if you look immediately above the breakpoint now on line 3900, you can see where we started the new interface thread, and the next thing we do is try and DQ a packet off the queue. And that brings us into this function called capture loop DQ packet. And you can see we've stopped just after we've accessed the queue, and I think what we've done there is just manipulated the call to actually DQ the entry, and we at this point will have a pointer to the actual packet content. So let's return back to the slides. Now what I'm showing here in this slide is just the main thread code that handles this dequeuing of the packets. So the capture loop start routine calls capture loop DQ, DQ packet, and then in that second function, capture loop DQ packet, that's where we actually handle the dequeuing. At this point here we can see we have this function call G async Q timeout pop unlocked. Notice the timeout value there. So if we go to the queue and there's nothing there, we wait for that timeout value before we would return, having actually perhaps popped no packets off the queue. The timeout is 100 milliseconds, which we can see defined at the top of this code. Having popped the entry from the queue, we then start to handle the actual packet. So we then call this function called capture loop write pcap ng callback, and we pass a pointer to the actual packet, and that function actually does all the work we need. In fact, it calls a couple of other functions, but it actually builds the packet and wraps it in the headers needed for an enhanced packet block, which is the pcap.ng format block for a packet, and then it writes that out to disk. So let's go back to the code and see what's going on here. Here we are stopped at the point where we're about to call capture loop dq packet to actually see if we have a packet on the queue. So let's step into that function and see what's going on. So the first thing we do is we grab a lock on the queue to make sure nothing else is accessing it, and then you can see here we're actually popping the entry off the queue just as we discussed with the timeout value set there. Stepping through, we then unlock the queue. We have the pointer to the packet content, and we come through to this point here, capture loop write packet callback. So this is where we're going to actually write the packet out, and you can see the pointer at the bottom, the entry that says queue element and then pointer to PD. That's the actual packet that we have in memory. So here we're in that function, the write function. We come through here and you can see that we have this next function call that writes an enhanced packet block, an EPB, just as we described in the slide set. So let's finish up by describing a couple of relevant parameters here. -B in the command line sets the kernel buffer size, so it's just that buffer size. And then we have two other parameters, -C and -N, that control the size of the pcap queue. If you don't specify those parameters, I believe there are default values, but anyway, you can vary the size of that queue and so control the amount of space that's used in the Dumpcap process address space. So it's interesting that the threads option creates yet another buffer, but this time in userland rather than in the kernel. And I guess it's debatable whether this is of a great help to us from a performance standpoint. So I hope you found that useful. See you next time.